Now, we've only proven this for tiny rectangles, right? Well, there's a curve enclosing a region, right? So all we do is we just break this into a grid. And we use more lines than this. You know, maybe we do a billion lines this way and a billion lines this way.
If we had the time, we would do that, of course, but right now we don't.
The what?
We would do that if we had the time, of course, but right now we don't.
Yeah. Well, yeah, if we did that, we'd need sharper chalk. Okay? Well, this represents what we're going to take a limit of as we approach zero, right? So let's just look at one of these little rectangles here. Now we're integrating around this rectangle like this, right? I shouldn't have made them so small, but we're integrating counterclockwise around every rectangle. Okay? Well, let's just look at what happens to all the rectangles that border this one. We're integrating counterclockwise around this one too, right? Which means we're integrating in this direction along this boundary, whereas here we were integrating in this direction, right? So that the integral over that boundary just goes away. Doesn't contribute anything to the integral over these two regions, right?
So only the integrals on the curve.
Yeah, well, the same thing happens, and that's very good. Okay? Okay, on each of these regions, the integral over the boundary it shares with this green region gives you exactly the opposite. So now, if we sum what we get over these little rectangles, we get the integral over this boundary, right? Well, then we can expand. And I think you see, because you said it ends up giving you the integral over the curve. There's a little detail there. But we do this one, right? And we can do this one. Anything that bounds one of these, we add it to the picture. And we see that we rapidly expand the region. The same thing happens, okay? And when we go to the next boundary, at least over here, we're going to end up with this, right? Now, this boundary here is going to take out what happens on this boundary, right? And the boundary below, well, will get taken out by one of the boundaries of this one, and we're just going to be left with this part of the curve. When we get out to the curve, the only thing that hasn't been canceled out is going to be what's on the curve. Then you take the limit as these things shrink to zero, and you're just left with the integral around the curve. Okay? So you can extend from one tiny rectangle to the entire curve. Now, I'll tell you this too, I like the text we're using, partly because it's open source. I can plagiarize it if I need to. But mainly, you know, I can do the problems, I can modify the problems. Okay? So that's convenient, but it's also well written and it's comprehensive. But they say the proof of Green's theorem is beyond the scope of the course. In every text I've ever taught out of, and the text I learned out of, and every time I've taught the course, I've had a text, and I've taught the course 50 times. Okay? No, actually in 47 years, a lot more than that. First course I taught in graduate school. I learned it, and I didn't think it was that difficult. Anything about it seemed particularly significantly more difficult than anything else you've seen in the course? I mean, you're able to make jumps. You know, you were able to tell me how to proceed in that proof at certain steps.
The craziest thing looking, but that proof is the integral with a circle on it. That just means what? Integrate all dx's and dy's in there or something?
Yes.
Well, you're just doing it, proving it. You know, it's not a trivial proof, but it's not that hard. I don't see it as being beyond the scope of the course. Now, when you get to Stokes' theorem, and even the divergence theorem, you kind of need a little bit of differential geometry to really do it right. So we're not going to prove those. And in any text I've ever taught out of, it said, this is beyond the scope of the course, but here are the theorems. And you understand them by analogy with Green's theorem, okay? They make perfect sense if you understand Green's theorem and think about them a little bit.